Good afternoon, everyone. My name is Anett Kondor, and today I will present surface energy and solid parameters measured by inverse gas chromatography. The structure of my presentation is on this slide. So first I will introduce iGC technique, and then I will show you some applications on surface energy analysis, and then about solubility parameters measurement. If this is the first time you hear about iGC technique, that's normal because iGC technique was developed in the 60s. And the first commercial iGC was released in 2000 by Surface Measurement Systems. It was called iGC-2000. And then SMS released in 2009 the first purpose-built iGC instrument. And you can see there was 40 years between the development of the technique and the first commercial instrument. So there wasn't marketing behind the technique and no sales. So it was really hard to hear about the technique. And also there wasn't internet available most of this time. Inverse gas chromatography is the most commonly and most successfully used technique for surface energy analysis of powders and fibers. iGC is designed to determine the surface energy and nevertheless suitable to measure different surface and bioproperties as well, like adsorption isotherms, heat absorption, glass transition temperature, diffusion coefficient, solubility parameters, and so on. On this slide, you can see the comparison between analytical GC and iGC. In case of analytical GC, the aim is the separation, and in that case, the solid phase, which is in the column, is known. You inject the different compounds, and these different compounds will separate along the column, and you detect them separately from the peak area and the retention time. You can get quantity and quality information about the injected compound. But in case of inverse gas chromatography, which is a reverse technique of the analytical GC, because in this case, what we investigate is the solid phase, which is in the column. We inject through this chromatographic column pure organic solvents. We measure the retention time of the different organic solvents on that solid sample. And from this retention time, which will indicate the interaction strength between the solid surface and the injected probe, we can determine different physicochemical properties of the solid, which was packed in the column. SMS iGC-SEA instrument is the first purpose-built iGC system, and it's designed to determine thermodynamic parameters, which is required for all the physicochemical properties of solids. Our column oven has a very precise temperature control. iGC-SEA instrument equipped with automated injection system. It also has a most sensitive detector for organic vapors, and it has all the necessary tools for the column packing. So this is the instrument. It has also safety features, hydrogen and organic vapor leak detector. This is the solvent reservoirs for the organic vapors. And the column oven has two column positions to run two samples sequentially. So here's again the instrument. So there's 12 interchangeable solvent reservoirs. It can inject a wide range of concentrations. It's like a headspace injection. Vapor phase is injected to the column. And there's different size of columns for the different materials, for the fibers, granules, powders, nano materials, and so on. We have also different types of columns: selenite, glass, quartz, and stainless steel tube. This is how a software looks like. Our instrument has also a CFR feature, so we can provide the software with the CFR 21 Part 11 compliant. On this slide, you can see the list of the different physical-chemical properties that you can measure with iGC system: surface energetics, acid-base properties, specific surface area, and so on. If you are interested in the technique, please visit our exhibition booth on the conference. Where all these properties can be useful, it can support research and development processes, because during research and development, to characterize your solid materials is quite important. And also, if you perform different modifications or functionalization on the solid, how this treatment affected the surface is important to know. You cannot use the instrument and surface energy and the surface properties to determine the batch-to-batch variability. You can also use all these surface properties to understand the behavior of a solid and to solve different problems, dissolution, dispersion problems. And you can also just use to characterize your solid materials to get more information about your solid. So first I will show you some studies on surface energy and surface energy heterogeneity. Surface energy correlates with other properties of your solid materials, like with cohesion, the process-induced disorder, and adhesion. You can see the surface energy, the total surface energy of solid can divide it to two components, the dispersive and the polar component, or the acid-base. It's the same. It's also called as acid-base. It means the same. And the surface energy quantifies the ability of the surface to react with the surroundings. And surface energy is used in everyday applications to improve our everyday life. For example, surface energy is also measured, and it's important in case of paper industry. The printing quality is strongly influenced by the structure and the chemical properties of the paper and the tuner particles. So both measured, and from the surface energetics of the paper and the tuner particles, the printing quality can be determined and also can improve the tuner particles. In building industry is also used because the materials which use the aggregates which use in the bitumen is also has to have a good adhesive properties. Surface energy is also used in medical care. Teeth has rather lower surface energy than the resins, the fillings, what they put in. So scientists designed the fillings to create a good bond with the teeth. The knowledge of the surface energetics is important in formulation design of multi-component systems and the prediction of processing performance. And the ability to measure surface energy of different materials is essential for ensuring compatibility between the given base material and the top coating one wishes to apply onto, or other materials one wishes to attach to this material. When we determine surface energy, we inject different organic vapors like a series of alkanes. And there's a developed method to determine the dispersive surface energy from the retention volume, the free energy of these alkanes. And if we inject the alkanes at different concentrations, we can determine the surface energy profile. And there's a more illustrative way to present the surface energy distribution. The surface uniformity, energetic uniformity is the distribution graph what we can generate from the profile. Because every surface is energetically heterogeneous. Real surfaces are often heterogeneous energetically. Besides the distribution of the different functional groups on the surface, there's defects, impurities, there can be pores, and there's other reasons why the surface energy on the surface energy heterogeneity. There's structural heterogeneity and chemical heterogeneity. Structural heterogeneity is like crystal imperfections, surface irregularities, and pores. Chemical heterogeneity contains the chemical degradants, surface impurities, contaminations, and so on. So why is it important to measure the surface energy heterogeneity? So not just to have a single surface energy value, a localized surface energy value. Because if you measure the surface energy heterogeneity, you can predict the flowability of your solid particles, the processability, dissolution, dispersion. Here's an example for the flowability study in case of dairy powders. We measured different dairy infant dairy powders surface energy heterogeneity, and as you can see, the IMF dairy infant milk powder had the most homogeneous surface energy profile. So it was very pure, the particle size distribution was very narrow, and also energetically the surface was uniform. And we also determined the flowability of these different infant milk powders with a Brookfield flow tester. And in case of the IMF milk powder, we measure the free-flowing behavior. So you can see there's a clear correlation between the surface energy distribution and the flowability of this milk powders. We published this results. You can see the reference on the bottom of this slide. So the publication was in the Food Chemistry Journal. And the next example for surface energy distribution is from additive manufacturing. The material was tungsten metal powder, and the supplier had the customer had an issue with one of the supplier powder. So one supplier metal powder had a different behavior. They observed dispersion issue, and they didn't know why, because the purity, the structure, all the physical properties of the three different metal powders, the source of the metal powders, was exactly the same. So we measured the surface energy heterogeneity, and we clearly distinguished, we could clearly see difference between the different suppliers sample. So supplier 3 sample had a higher surface energy, and the surface energy distribution was higher, so probably this sample processed differently. In the next couple slides, I will show you some solubility parameters data. In the iGC-SEA software, we implemented all the 3 different available methods for solubility parameter analysis: the classic Hildebrand, the Hansen solubility parameters, and the solid partial solubility parameters. The classic Hildebrand solubility parameter based on this equation. Solubility parameters can be used for drug delivery, formulation, storage stability, coatings, and so on. This is how it looks like in our software, this application. And we have some application notes when we determine the polymers and PMMA solubility parameters using this method. On this slide, you can see a PMMA solubility parameter. What we measured is 19.08 megapascal square. And it was measured at 363 Kelvin using different organic solvents. And the measured solubility parameters matched with the literature values, what we found. The Hansen solubility parameter set contains the three different contributions: the dispersive, polar, and the hydrogen bonding component. To determine all these different contributions, you need to inject different organic vapors like alkanes for the dispersive, for the polars, aromatic hydrocarbons, ketones, and so on. For the hydrogen bond, alcohols, pyridine, which can create hydrogen bond interactions on the surface. This is how it looks like the Hansen solubility parameters in our software. And the Hansen solubility parameters used in pharmaceutical industry to predict oral absorptions or release rate. There's a very nice publication from one of our customers which determines the solubility parameters of biomedical polymers, and the reference is on this slide on the bottom. Measurements, temperature, and the coverages varying between these different methods, solubility parameter methods. For the 1D and the 3D, so the Hildebrand and the Hansen application, you have to measure the different vapors on the surface at the glass transition temperature or close to the glass transition temperature. And for the next application, what I will show, you don't have to be at the glass transition temperature. You can be below the glass transition temperature points or above. And for solubility parameters measurements, the coverage has to be between 0.20%. This is how much the surface is saturated with the injected probes. So you have to be in the infinite dilution range. The last application I will show you what we recently added to the software is this SCHNERKARGER model. And you can see this is how it looks in the software. So the HSP is the latest model. This method is based on the absorption energy of different organic solvents, which is related to the solubility parameters. And the Hansen solubility parameters of the solid can be determined by multilinear regressions of these equations. Here's an example for these applications, for this method application from one of our customers. And the influence of nano-oxide modification on the solubility parameters can be seen on this results. So the different samples, hematite, goethite, and the filter cake, you can see how the solubility parameters changed with the different modification. Very challenging in case of solubility parameters, the probe selection. Of course, more the better. But however, time is money in business, and we know that industry wants to have quick answers. The best way is to use the extreme probes, so the one which is strong acid or strong basic. And of course, some properties of solid can help to choose the appropriate probes. The molecular structure is one of that, for example. And in case of like one sample PEG, which interact strongly with alcohols, but has weak interactions with alkanes, the recommended probes are the different alcohols and just a couple alkanes. Also, you can see in the publications which are available a list of different probes, but other people suggest to use for the solubility parameter analysis, and also the software contains the different parameters of the solvents in order to help you to select the right probes. And finally, to summarize my presentation, iGC-SEA instrument can help you to understand and investigate processing performance of your solid material, the process-induced disorder on the surface of the different solids. Also, you can investigate processing behaviors. Batch-to-batch variability can be also measured and monitored. Surface properties measured by iGC is at a condition of processing and application of the solid product. Thank you for your attention, and please visit our booth if you have questions or if you get interested in the product. And my colleagues in Japan happy to answer your questions. Thank you again, and have a nice day.